Hello there. This fourth Pharmacokinetics video is about remedy metabolism. We'll cover phase 1 metabolism of drugs and herbal constituents, phase 2 metabolism, and the factors that affect metabolism. Metabolism can be described as the biochemical transformation of one substance into another, and metabolic processes are catalyzed by enzymes. Therapeutic substances like conventional drugs and herbal constituents are secondary compounds. They're not dealt with by the body as primary nutrients, but instead they must be treated as foreign biologically active substances, otherwise known as xenobiotics. In the metabolism of therapeutic substances, phase 1 involves the addition or exposure of reactive functional groups via oxidation, reduction, or hydroxylation. Phase 1 may be skipped in the metabolism if the molecule already has a reactive group. Phase 2 involves conjugation of another substance onto the reactive metabolite, and phase 3 involves excretion, which we'll not dwell on today. Most remedy metabolism takes place in the liver hepatocytes using relatively few different types of enzyme, which are fairly non-specific in their substrates. Some metabolism also takes place in the plasma, the kidneys, and the lungs. Also, the gastrointestinal tract is another important site of metabolism. In the gut lumen, digestive enzymes play a role, as do the actions of gut microorganisms. Intestinal cells themselves also actively metabolize remedies. There can be a limited capacity for metabolism of these xenobiotics. Clearance mechanisms are increasingly saturated as remedy dose increases, so that the capacity to decrease xenobiotic availability is less efficient at higher doses. The capacity for clearance may suddenly be overcome if the dose reaches a threshold level. There can be significant, so that means there can be significant differences in potencies between very similar doses of a xenobiotic, be it a drug or a herbal remedy. So let's look in more detail at phase 1 metabolism. Phase 1 metabolism involves the oxidation, reduction, or hydroxylation of the xenobiotic compound using enzyme systems of the cytochrome P450 family, which are bound to the endoplasmic reticulum. Now, we've come across cytochromes before when we've been looking at the energy pathways of respiration. They're isoenzyme proteins, so-called they're called cytochromes because they give a red colour to the cells containing them, and this is because they contain a heme group, which consists of an iron 3 ion held in a protoporphyrin prosthetic group. Cytochromes act in concert with cytochrome reductase enzymes. The overall effect is to add reactive groups to the xenobiotics. In this diagram, the xenobiotic is denoted as R. So first of all, NADPH reduces the reductase enzyme, which in turn reduces P450, which can then, in this case, hydroxylate the xenobiotic, so adding a hydroxyl group. The whole process requires energy in the form of the NADPH reducing power, and it also requires oxygen as the ultimate hydrogen acceptor. If the xenobiotic substrate for this reaction is a therapeutic drug with a narrow therapeutic window, two problems could arise. Inducing the drug metabolism by P450 will reduce the efficacy of the drug, and inhibition of the metabolism could increase toxicity by increasing the drug availability. Now, there are several types of P450, for example CYP3A4, which is involved in phase 1 metabolism of many drugs, including warfarin and oral contraceptives. CYP3A4 induction by hypericum can compromise warfarin therapy, and there's a theoretical risk of a suboptimal contraceptive dose if there's concomitant use of St John's wort and the oral contraceptive. I say theoretical, there's no clinical evidence that this actually takes place. One of the advantages of phase 1 xenobiotic metabolism is that it turns some drugs into their active form. A disadvantage of the phase 1 pathway is that it produces reactive substances which could harm the tissues. So it's just as well that phase 1 prepares xenobiotics for phase 2 of remedy metabolism. Some xenobiotics have reactive functional groups already, and so are metabolized directly by the phase 2 mechanisms. Otherwise, phase 2 metabolism works with substrates which have already been activated by the cytochrome pathway. So phase 2 accomplishes the next stage of metabolism by conjugation. This is the addition of a similar sized compound, and forgive the spelling mistake there, to a xenobiotic at the reactive group of that xenobiotic. Conjugation makes xenobiotics compounds less reactive and thus safer for the body. And it also makes them more water soluble and so more easily excreted via bile and urine. There are at least 6 different phase 2 metabolic pathways, each using different conjugates and different enzymes. This first mechanism adds glucuronide, a compound of glucose and the nucleotide uracil. So this glucuronide is added to the xenobiotic, depicted here as ROH. So you can see that hydroxyl group is replaced by this whole complex, and UDP is got back again. The enzyme sulfotransferase adds a sulfate group to xenobiotics, transferring it from another complex nucleotide. Methylation involves the addition of a methyl group, or CH3, and this is transferred from S-adenosyl methionine, abbreviated to SAM or SAM. This is a very important detoxifying mechanism. Acetylation by acetyl-CoA is an important way of dealing with xenobiotics which possess amine or NH2 groups. Products of that acetylation pathway, for example, this one, R1CO CO2H, can be conjugated with another aminated xenobiotic, R2NH2. and this can produce R1 CO2 NHR2. So R1 is the first xenobiotic, could be anything, well, lots of things. R2 is another xenobiotic, could also be lots of things. So this is pretty neat really, because it means that you've got two poisons which you then link together with a CO2 group, and this effectively kills two birds with one stone. You've got rid of two things at once. Very efficient. Lastly, GSH transferase enzyme transfers sulfhydryl group SH from glutathione to xenobiotics, making them less harmful and easier to dispose of. Now, in this case, glutathione is lost from the body in this pathway. In all the other previous pathways, the carrier molecules are free to be reloaded with the respective reactive functional groups. And note the similarity in a lot of these processes of phase 1 and phase 2 xenobiotic metabolism to the metabolic processes that you saw involved in energy production, using reduction, oxidation, cytochromes and nucleotides. So arguably the processes of respiration may have evolved originally to deal with that pesky toxin called oxygen, and the cells have found a way of deriving energy from it. Detoxification can produce energy in certain cases. You'd have to check, but that may be why some rats are able to thrive on rat poison. And certainly many microorganisms can make a living from metabolizing compounds which are toxic to everyone else. So taking phase 1 and phase 2 as a whole, certain factors can influence its rate and efficiency, not least the individual variation in the number of enzymes made. Induction of xenobiotic metabolism will increase the clearance rate of their substrates. So common inducers include a whole range of poisons that we're exposed to, both by mouth and by absorption or inhalation. Inhibition of metabolic pathways by certain drugs or even grapefruit can reduce drug clearance, giving higher circulating concentrations of the drug, sometimes making them more potent and giving more side effects, but also making them persist for longer. Liver disease will only affect xenobiotic metabolism if it's severe or advanced, because the liver has quite a lot of spare capacity. And finally, the very old and the very young may lack sufficient liver enzymes to cope with xenobiotics, so we should reduce herb and drug dosage for both groups and or give agents with a lower risk of toxicity. Thank you.